would break a bit because you have more cross flow. Or flow. Okay. Remember that this other heat source has to come from somewhere. I like food. All right. So back to me. This is called the LA type. In Denver, you get a different sort of inversion layer. In Denver, your basin is surrounded by mountains, and those mountains are really tall. This is also Mexico City, to a lesser degree, Guatemala City, Lima, Peru. Where was the other one that I said I could explain? Buenos Aires. Buenos Aires is going to be like Lebanon and other marine influence. So here, in Denver and other high elevation valleys, the cold air is not provided by the ocean. It is the nighttime sinking cold from the snowy mountain tops. You guys know what cold air halls? So that basin will fill up with cold air falling off the mountains. It comes down rivers, down canyons into that valley, so it fills up with cold air, and then the hot air from the desert will cap it off, and you get an inversion layer. This is what happens in Mexico City. Yes. It doesn't have to be snow, it's just higher elevation mountains around it. Am I mistaken that Mexico City is surrounded by mountains?
No, well, there are some mountains.
I have been told that it's in that category where it's actually even the textbook says it.
Why is there smog at the top? Like if you go and that's what there's still smog at the top of the mountain.
Probably because you're not at the highest mountain, I'm thinking. Like here in LA, the highest smog level is when you're right at the pass. Because the passes let in the hot air, so that's the lid. And as soon as it breaks up, it all goes out the same way. So the worst place to live is in Cajon Pass or San Bernardino Pass, the places where, no, it's the same. San Gabriel? I don't remember. Cajon Pass or the other one. Because the problem here is that that's where the hot air is at that pass altitude. So the place that you're referring to in Mexico, I haven't been to Mexico City, so I don't really know. But I'm guessing that the place you're referring to is at roughly the altitude of the passes, and so that's actually where the cap is. If you went higher than that in the mountains, you'd be above it. Yeah.
Does the LA example with the passes between the mountains does it help with smog, or does it have anything to do with it?
So the passes are the inlet for the incoming hot air. So that sets the elevation for the smog layer. Hot air don't sink.
Okay.
So you won't get that hot air lower than the passes. And so if you live at or just below the passes, that's where the smog will be, kind of piled up right below the hot air. Make sense? Yeah.
So on that picture there,
yeah.
The warm air is at the mountain level.
Exactly. That's the notch in the mountain, but it's not through. That's pass elevation.
And then the cold air is like really, really far.
Higher than that. Yeah. Watch this picture. This is not the densest smog I've ever seen, but you can tell that there's still a little bit of mountain just above those.
Yeah.
That's the mountain above the pass elevation.
Okay.
So that mountain that you see in the background is like this, above the smog.
Yeah, drive back from LA on Saturday, like you can see mountains.
I can try to show you a photograph that someone just sent me this morning.
Yeah, this weekend it was really bad. It was like brown clouds.
Yeah, that doesn't surprise me at all.
Is
the smog mainly CO2?
Smog is not CO2, and we'll talk about what's in the smog in just a minute. I'm trying to see if I can get this up on the screen for you, but maybe not from this. So, I don't know if you guys can see this from where you are, but the smog has blocked off all but the tops of those buildings. It's the exact same view. Ava took this.
Yeah.
So you can see the same mountains as I see in my photograph, except in her case, downtown is covered with smog except for the tips of the Columbia building and a couple of those others. And again, that is the height of the passes in the basin. So everything below pass height is smog. At pass height, you have the hot lid. Above pass height, you have the natural dissipation of pollution. I'll try to get this up into the PowerPoint. I just got this last period. So. Okay. Maybe from here I can get it into. No, I guess not. Sorry. Okay. So let's talk about what's in here. Our atmosphere always has oxygen. We've got a sun, so our atmosphere will always have ultraviolet. It's fog, so it'll always have water. That's all provided by our atmosphere. So if you got water, oxygen, and ultraviolet, the question is which ingredients are we going to use to mix with those? There's two different types of smog. They're called sulfurous and photochemical. You've got SOx and water in the atmosphere with ultraviolet and oxygen to make acids. That's what's in London. It comes from burning coal. That's the source of the SOx. And that one is gray. This is the gray kind. The other type is photochemical. That's NOx and VOCs, like this, to make the oxidants, like LA, Denver, Mexico City, and those come from cars. That's the brown kind of smog. And then there is the possibility of the double whammy, which is when you've got cars and coal in the same air. Beijing probably has the world's most toxic air today. What's that? Yeah, and those mixed together basically make Godzilla, because you've got oxidants and acids in the same environment. Your lungs have very bad chances of doing well. By the way, in Beijing, on top of that beautiful mix, they mix in a lot of particulates to make sure that no one will survive.
Yeah. So are they, like, they've got a lot of national attention to this, like, coral pollution. Are they trying to do anything about it? Or
Yeah, apparently the peak in bad air quality was 2008.
So, like, what are they doing?
I wish I knew better, but I'm sure you can just Google this.
They planned that for the Olympics.
They what?
They planned that for the Olympics. Then the other athletes would have a worse chance for all their athletes training in.
Ah, very cheeky. Okay. Anybody want to talk more smog? Because I don't. Hey, bro. Look at this. I'm going to knock on the door. It's going to be awesome. Okay. So let's see if we can't control air pollution. You'll need to know about 1, 2, 3, 4, 5, and we're going to add a 6th air pollution control. I'm guessing you already drew these because I asked you to draw them at the beginning of the period. So I'll probably just be able to talk about them. I'm sure that none of you are coughing. It's not why you're all manically wriggling your pencils. The first and most basic and probably most effective air quality control ever was the invention of the chimney. It just gets the air pollution further from the humans, and really, that's kind of a big accomplishment. That's probably saved more lives than all the other stuff. Because obviously the alternative to that is just the worst possible scenario. So at least getting the pollution a little higher from you, that makes it rise better because it comes out really hot, but the air at 30 feet higher is a little bit cooler, so it's got a better pressure differential. Just takes off. If you can just get it 30 feet up in the air, you've done 90% of the battle. But then if you really want to control it, not just locally, but actually capture stuff, we get into particulate controls. A bag house or a filter works the same way as like the bag inside a vacuum cleaner. It's like a screen, and so you push the air through the screen, and the particulates are caught by the screen, but the air squeezes through. When it gets clogged, you just turn off the air for a minute, shake out the bag, and now you've got all your particulates in a container so you can take them to landfill. That make sense to everybody? Settling chambers or cyclones are mechanically moving the air and then letting the particulates fall with gravity before you let the emissions out. So settling chambers will sometimes have a flap. So you fill it up with smoke and then you close it, let all the ashes settle, then you let that air out with all the ashes being in the bottom. Or another option is what's called a cyclone, where you spin the air around so it gets centripetal force, and on the edges you trap the particulates, and then they'll just kind of snowball down to the bottom. There's also this cool option called an electrostatic precipitator. Where you apply a charge to the particulates, and then you use the opposite charge to trap them like a magnet. So you magnetize them first, and then you use the opposite charge to work like a magnet. That's really cool. Yeah, and you know, there's like a really simple demo you can set up for this. By the time I get to this point in class, I'm always running low on time. This year I thought I would do it, and then we ran into this 4-week, 3-week problem. But there's like a really simple demo that you can do. It involves a hair dryer, which creates static because of the way that it makes the air move. And then you can make like a little fire with pieces of toilet paper. And then you use like a tube from a paper towel roll over that fire, and what do you call it? Hair dryer on that tube, and you put a magnet on top, and all your dust will stick to the magnet. It's kind of neat, same idea.
What's before the apply charge with those little red?
That's the particulates. You can see I've drawn them in red so that you'll see the pollution.
I thought it was like plus.
Oh, might be done. So these are all red dots. Now they're pluses.
Okay.
And so they've gone from being uncharged to being positively charged. And by the way, that charge is not one way or another. You can apply a negative charge and trap them with a positive. You can apply a positive charge and trap them with a negative. Yeah?
Just say in that second chamber.
This one says apply charge. This one says opposite charge. Trap them. Finally, to control stalks, you spray them with water and limestone. This is water and calcium carbonate. anybody know if that's calcium carbonate? Help further out, is that calcium carbonate?
Well,
With a tube?
what's the subscript after?
CO2 or CO3? CaCO. CaCO